Welcome to AI Paper Podcasts. We dive into the latest research so you don't have to wade through it all yourself.
Yep, giving you the key takeaways and what they actually mean.
And today, we're tackling a really big one. A question that feels, well, fundamental. How much do these huge language models actually memorize from their training data?
It's something everyone asks, right? Privacy, copyright, weird outputs. It all touches on this idea of memorization. But what is memorization really in this context? It's slippery.
Totally, which is why this paper we're looking at today is so interesting. It's called How Much Do Language Models Memorize? Researchers from FAIR, DeepMind, Cornell, NVIDIA, the usual suspects.
And they propose a whole new way to think about it based on information theory and compression. They even find a specific number, like a capacity limit.
Exactly. So, quick summary up front. This paper defines memorization as how much better a model compresses data it saw versus data it didn't. They find models like GPT have a capacity around, 3.6 bits per parameter?
Right. And this capacity limit seems to explain why models sometimes get better when you give them more data than they can possibly memorize. That's the double descent thing. It forces them to generalize.
So that's the core idea. We're going to unpack how they got there, what it means for generalization versus just remembering stuff, and even what kinds of things do get memorized.
Let's do it. So before this compression idea, how did people try to measure this?
Good question. The paper mentions a couple of the standard approaches, like extraction.
Right. Can you trick the model into spitting out exact training data? You give it a prompt, maybe the start of a sentence?
Yeah, like the first half of my unique social security number example from the training set, and see if it completes it correctly.
Exactly that kind of thing. Though hopefully not SSNs. And the other main one was membership inference.
Okay, so that's different. That's trying to figure out if a specific piece of text, say a sentence, was actually in the training pile or not. Maybe by looking at how surprised the model is by it, like its loss.
Precisely. Was this data point part of the training, yes or no? Extraction is get it out, membership inferences, was it in?
Gotcha. But the paper argues these aren't quite hitting the nail on the head for understanding, the difference between real memorization and just being good at language.
Yeah, they have limitations. For instance, a model might generate something that looks like memorized training data, but it could just be really good generalization.
How so? Give me that example they used.
The paper talks about calculating, say, 2 to the power of 100. A big model might give you the correct, very long answer. But it's super unlikely that exact number sequence was written out in the training data.
Right.
The model didn't remember it like a factoid. It generalized its understanding of math, of powers, of how numbers work.
Ah, right. It's applying a learned skill, not recalling a stored item. That's a crucial difference.
It really is. And, other things muddy the waters, like extraction sometimes works better or worse depending on how you ask the model of the decoding strategy.
Yeah.
That feels fragile. If memorization depends on the questioning technique.
Yeah, you want it to be about what the model knows, not just how you happen to query it.
Exactly. And some studies even showed models generating stuff that looked extracted but definitely wasn't in the training data. Just pure generalization, creating plausible sounding but novel sequences.
So the old methods struggle to cleanly separate, remembering unique training examples from just being good at predicting likely text. And often they weren't very granular, like telling you how much a specific example was memorized.
Right. Which brings us to the paper's big idea, defining memorization using information theory, specifically compression.
Compression, like zipping a file. How does that relate?
Well, think about it like this. If a model really knows something specific about a data point, it should be able to represent that data point very efficiently, right? It shouldn't be surprised by it.
Okay. Less surprise means more predictable.
Yeah. Or more compressible. If having the model lets you describe or encode that data point using fewer bits than describing it without the model, that difference tells you how much the model knows specifically about that data point. It's inspired by ideas like Kolmogorov complexity.
Interesting. So memorization is defined as the extra compression you get on a data point because you have the model.
That's the core concept. They formalize it using the model's likelihood, PX says, the probability it assigns to the data point X given its parameters. Higher likelihood means lower loss, means better compression. They use this HK term, Holder-Kontsevich entropy, which is related to loss.
So lower loss on a specific point implies it's more memorized in this compression sense. Wait, models get low loss on things they generalize well to, too. Like our math example.
Yeah.
So they split that apart.
Good point. That's the next crucial step. They formally distinguish between
Okay.
1. Unintended memorization. That's information tied specifically to the training data set itself. the random details, the specific phrasings it happened to see.
The stuff we worry about for privacy and copyright.
Exactly. And 2, generalization. That's information about the underlying true data distribution. The rules of grammar, common sense facts, how language generally works, the stuff we want it to learn.
Okay, so learning dogs bark is generalization. Remembering my specific dog Fido barked exactly like this at 3:17 p.m. yesterday. If that specific sentence was in the training data, leans towards unintended memorization.
Perfect analogy. And to measure just the unintended part, they do something clever. They compare the model's compression of a data point not just to 0, but to a hypothetical reference model.
A reference model, like what?
Think of it as an ideal oracle model that knows the true underlying distribution perfectly, trained on infinite data. The extra compression the actual model achieves beyond what this perfect oracle achieves is attributed to knowing the specifics of the finite training set it saw. That difference is the unintended memorization.
Wow, okay, so it's not just how well does the model compress this, but how much better does it compress this than an ideal generalizer would. That isolates the dataset's specific knowledge.
Precisely. It's a neat theoretical trick to try and separate those two kinds of learning.
All right, so armed with this new definition, they could start measuring things, which leads to that capacity limit finding. How did they pin that down?
This was a really cool experiment. To measure only memorization, they needed to eliminate generalization entirely.
How do you do that?
You train the model on data with no patterns, completely uniform, random bit strings, just noise.
Random bits. Okay, yeah, there's nothing to generalize to there.
Exactly. The only way the model can possibly improve, get lower loss, or compress this random data is by literally storing the specific sequences it saw. Any learning is memorization in this setup.
Clever. It forces the model to show its pure storage ability.
Right. So they trained different sized models on different amounts of this random noise. And what they saw was, well, the amount memorized went up linearly with the amount of data shown.
Makes sense.
Up to a point. Then it just flatlined. It hit a ceiling, a maximum capacity for how much random junk it could store.
A hard limit. And did that limit depend on the model size?
Yes, it scaled with the number of parameters. And the big number they found, the headline figure, is that these GPT-style transformers seem to have a capacity of roughly 3.6 bits per parameter for this kind of pure memorization.
3.6 bits per parameter. Wow, that's specific. So a billion parameter model has about 3.6 billion bits of this raw memorization headroom in this context.
Right.
Why should you, listening, care? Because it suggests a physical limit baked into the architecture.
Yeah, it's a concrete number. They found it was generally between 3.5 and 4 BPP. They also checked different precisions, like bfloat 16 versus float 32.
Did using more bits per parameter double the capacity?
Interestingly, no. Going from 16-bit bfloat 16 around 3.5 BPP to 32-bit float 32 around 3.8 BPP didn't nearly double the capacity. So those extra bits in float 32 aren't purely buying more raw memory in this sense.
Fascinating. So there's a quantifiable limit, but that was on random noise. Models train on real text, right? Where generalization is the goal.
Absolutely. So step 2 was repeating these kinds of measurements using real text data, specifically the fine web data set.
Okay, now generalization can happen. What did they see then? How did memorization and generalization behave?
Well, as you might expect, unintended memorization still generally increased with model size. Bigger models can store more specifics if they need to.
And with data set size.
Right.
More data, more memorization.
Initially, yes. As the model sees more unique stuff, it memorizes more. But, and this is where it gets really interesting, as the data set got very large compared to the model's capacity, the amount of unintended memorization actually started to go down.
Hold on. You feed it more data, and it remembers less specific stuff from the training set. That sounds backwards.
It feels counterintuitive, but think about that capacity limit. If the data set size grows way beyond what the model can physically store using that 3.6 BPP per parameter, it can't afford to waste capacity memorizing every single detail anymore. It's like its memory budget is full. So it's forced to find more efficient representations patterns that cover lots of examples.
It has to prioritize. It shifts from storing individual items to storing the general rules. It starts generalizing more.
Exactly. It substitutes sample-specific details for broader, compressible patterns. The generalization starts to dominate because it's a more efficient use of the limited capacity when faced with vast amounts of data.
Okay, that makes sense. Limited capacity forces a trade-off towards generalization when data is abundant.
And this trade-off, this dynamic driven by the ratio of data size to model capacity, gives a really elegant explanation for something that's puzzled researchers for a while. Double descent.
Right. Double descent, that weird phenomenon where you make a model bigger or give it more data, and performance gets worse for a bit, then suddenly it gets much better. That dip in recovery.
Yeah. What they found was that the point where performance starts getting better again, the second descent, happens pretty much exactly when the data set size exceeds the model's capacity, calculated using their 3.6 BPP figure.
Whoa.
Their theory is, below that capacity threshold, the model can just memorize the training data, noise and all, which hurts generalization on unseen test data. But once the data amount swamps the capacity...
It can't memorize everything anymore.
Right. It's forced to ditch the noise and find the underlying signal, the general patterns. That's when test performance dramatically improves again.
So the capacity limit isn't just some abstract number. It seems to mark a critical phase transition in learning, explaining that double descent curve. It's a point where the model must generalize effectively. For you practitioners, this helps explain why huge models need truly massive data sets to hit peak performance. You need to push past that memorization-heavy zone.
That's the compelling story their results suggest, yeah.
Okay, so if models generalize more when data exceeds capacity, what does that mean for extraction attacks? Can you still pull training data out?
Well, they found it's not impossible, but the reason you can extract something changes. On these very large data sets, even when they could successfully extract a sequence, it was often attributable more to generalization, meaning the extracted sequence wasn't necessarily some obscure fact the model specifically stored, but rather a sequence that was just highly probable given the general patterns of language it learned.
So it might generate something from the training set, not because it remembered that specific instance, but just because it's a very common or predictable phrase or sentence based on everything else it learned.
Exactly. It's well compressed by the generalized knowledge, not necessarily unique memory. So successful extraction doesn't automatically equal problematic, unintended memorization of a specific sensitive data point. It's more nuanced.
That makes sense. But what about the things that are highly memorized, even in this generalization-heavy regime? Did they find anything special about which data points the model holds onto most strongly?
Yes, and this was another really surprising result. They carefully deduplicated the data set first, mind you.
Okay, so not just repeating common phrases.
No, they looked at the individual training examples with the highest measured unintended memorization, and they found a strong link between high memorization and examples containing rare words.
Rare words, not common words or duplicated sentences.
Not duplicates, because they removed those. It was about statistical rarity across the whole data set. They used TF-IDF scores termed frequency inverse document frequency. High TF-IDF means a document has words that are rare overall in the data set.
And those were the most memorized.
Significantly more likely, yes. It seems the model uses its limited unintended memorization budget on the statistical outliers, the sequences that are hard to explain using its general knowledge.
That is really fascinating. It's like it prioritizes remembering the exceptions to the rules it learned.
That seems to be the case. They even gave an example. Some Japanese text within their largely English dataset had a very high TF-IDF score and was among the most memorized sequences. Looking at the top memorized examples, many contain non-English text, Japanese, Chinese, Hebrew things that are statistically uncommon tokens in that specific dataset.
So the model is spending its precious memorization capacity on the weird stuff, the bits that don't fit the general patterns easily.
That's a great way to put it. It allocates that capacity to what's least explained by generalization.
Okay, switching gears slightly. How does all this affect membership inference? Can we still reliably tell if a specific data point was in the training set?
Well, as we saw, if the data set is huge compared to capacity, the model generalizes more. This makes training examples look less distinct from unseen examples in terms of their loss or compressibility.
Right, the signal gets weaker. The difference between seen and unseen shrinks.
Exactly. So membership inference gets harder. And they formalized this too. They actually developed a scaling law.
A scaling law for membership inference?
Yeah, a formula predicting MI performance. They use the F1 score, which balances finding true positives and avoiding false positives based on the model's capacity, that 3.6 BPP, and the data set size.
Did they test if this formula holds up?
They did on models up to GPT-2 Medium and XL, and found it predicted the difficulty reasonably well.
Okay, and what's the punchline from this scaling law for today's huge models trained on web-scale data?
The prediction is pretty stark. For these very large models trained with high tokens per parameter ratios, reliable loss-based membership inference on an average data point might just be fundamentally infeasible.
Wow. So for a typical sentence in a massive data set, It might be practically impossible to tell if it was training data just by looking at the model's loss on it.
That's what the scaling law suggests. The generalization is so strong and the data set so vast relative to capacity that the average training example just doesn't stand out enough anymore based on loss alone.
That's significant. It doesn't mean MI is impossible. Maybe other methods work, or maybe those rare, highly memorized examples are still vulnerable.
Absolutely. It specifically applies to loss-based MI on average examples, and their framework is actually useful for finding those potential outlier vulnerabilities.
Okay, let's pull this all together. Quick recap of the key things we learned today from this paper. First, a new definition of memorization based on compression.
Yep, separating it from generalization using that reference model idea. Second, finding that concrete capacity limit around 3.6 bits per parameter using random data.
Third, showing how on real text, memorization decreases and generalization increases when the dataset size swamps that capacity.
Fourth, linking that transition point directly to explaining the double descent phenomenon. It's when the model is forced to generalize.
Fifth, extraction often reflects generalization of probable sequences, not just specific recall, especially on large datasets.
And sixth, the surprising finding that highly memorized points, even after deduplication, tend to be the statistical outlier's rare words, foreign text.
And finally, the scaling law suggesting traditional membership inference is becoming very difficult for average data points on large, modern models.
So for you, the listener, this gives a much more nuanced picture than just models memorize everything or models only generalize. There's a measurable limit, a trade-off.
It changes how we might think about privacy risk. Perhaps the focus shouldn't just be on average data, but on identifying and maybe mitigating those statistically rare, potentially sensitive outliers that do get memorized more strongly.
And it reinforces the idea that effective training involves balancing model size and dataset size to push the model into that beneficial generalization-focused regime past the capacity limit.
All right, here's a final thought to leave you with, thinking about those rare, highly memorized data points. If models have this finite 3.6 BPP capacity for unintended stuff, and they prioritize statistical oddities when that capacity is stressed, what does that mean for learning equitable representations? Does it mean common knowledge might get generalized away while the memorization budget gets spent on the exceptions or niche data? Or does it just highlight that we need to ensure common important patterns are really, really well represented so they become part of the robust generalization?
Yeah, and what about data that's sensitive because it's rare or represents a minority group? Does this mean it's paradoxically more likely to be memorized in this unintended way? The privacy implications there could be complex.
Definitely something to chew on. How architectural limits and data statistics interact to shape what's actually learned and retained.
A fascinating area.
Absolutely. Well, that wraps up our look at this paper on language model memorization for AI paper podcasts. Hope you found that useful.
Thanks for tuning in.